Good morning, my friends. Today we are going to talk about some more laboratory shear strength testing, and I'm going to introduce you to one of my favorite laboratory shear strength tests called the triaxial shear test. Now, I know that probably each and every one of you has gone down into the soils lab for your lab sections and at one point or another looked at this device that you're seeing right here, this picture of, and wondered, what in the world is that thing? And that thing is a triaxial shear test device, and it's what we're going to talk about today. The triaxial shear test device has a lot of advantages that we'll discuss, but for some background, let's get in and just review a little bit about the direct shear test. You'll recall, if I look at a cross section, the direct shear test, if I look at maybe a still box and I take a cross section through the still box, and then so it's hollow and we fill the thing up with sand. So for me, yellow always means sand. There we go. So I filled this thing up with sand, and then what ends up happening is, this base is fixed usually, and then we have a mechanism that's going to pull the top. We also have a mechanism that applies a confining stress to the top so that we stress the sand in the vertical direction. And then as we start pulling, what's eventually going to start happening is we're going to develop a shear plane through the sand where eventually this upper portion of the test is going to start sliding relative to this lower portion, and the whole point being that we want to develop points along the failure envelope so that we can get the friction angle phi. That's the whole reason we do a direct shear test. Now, we've talked about a couple of problems with the direct shear test, but I want to re-emphasize a few of them. So here's this sand, right, as I'm outlining it right here. And the whole idea is this sand is really supposed to try to mimic some soil element that's in the ground. So we are applying a vertical stress. That's good. But that's about all that is good. Because after that, the element that's in the ground, it's going to have some horizontal stresses acting on it too. But do you see any horizontal stresses being applied to the soil in this test? Not really. I mean, we're applying a shear stress, but that's not the same thing as a horizontal confining stress. And so there is no horizontal confining stress being applied to this soil sample. So we don't have any of that going on. In addition, if I load this soil sample up a whole bunch, we learn from Mohr-Coulomb theory that a failure plane is going to try to develop that's going to be equal to 45 degrees plus phi divided by 2. But this angle right here of this failure plane is completely flat. It's completely horizontal. So the fact of the matter is that soil doesn't like to fail in the horizontal plane on its own. In fact, it never does, except at the very bottom of, like, if I have a slope stability failure, there's going to be a portion at the bottom of this rotational failure that is failing in the horizontal plane, but that's about it. Everywhere else is going to be inclined or even approaching vertical, like up here. So the final thing is we do know that there's going to be shear stress along this plane. But what about up here in the corners? Is there shear stress, or down in these corners? Is there shear stress in the soil in those parts of the test? And if the answer, of course, is no. So what we have is non-uniform stress distribution throughout our soil sample in the direct shear test. So these are problems that can be eliminated if we do a triaxial shear test. So here's a little diagram or a sketch of what the triaxial shear test looks like. And the whole reason that we have a triaxial shear test is so that we have greater control over the confining stresses and the stresses that we use to load our soil and simulate the induced stresses that we as engineers are going to apply in the field. So what we end up having here, let me change my color. The soil sample sits inside a closed chamber, and the closed chamber is filled with water that completely surrounds the soil, okay? And then what happens is we have, actually, let me change that to red. We have, on the cap of the soil, we have essentially what we call the ram, or the actuator. I like the name the ram. It sounds like a medieval torture device or something. Bring out the ram. Sorry. So we apply the ram to the soil, and once the soil gets situated and set, we start to squish it with an axial load, and we start to measure its shear strength. Now, the soil itself is sitting inside a closed membrane. So it's not like it's just free to unravel and be eroded down into the water. It's completely confined by this membrane. And so all it feels is pressure from the surrounding water. But it doesn't necessarily feel the water itself. What's really cool is that we really have one system inside the soil, and then we have a second system outside the soil. So we can control the pore pressures and what's going on in this system, but have it be completely separate from the pore pressures and things going on in the system inside the membrane. And so water can leave through the drains as it wants to, or it can come in through the drains if the soil is trying to dilate and expand the pore volume in it. And so the soil is free to kind of do that. And then, of course, this axial load that we're going to apply, this is going to mimic or simulate the induced stress. So the cell pressure, this is supposed to, this is the gauge, of course, but the cell pressure is supposed to mimic the geostatic stresses that are in the ground already. So at the end of the day, really what we're after, folks, is to try to get the soil to feel as comfortable as possible, to trick it as if it's back in the ground and everything's okay, and the whole sampling and extraction from the ground and transportation to the lab was just a bad nightmare, but it wasn't real. That's what we're trying to trick the soil into doing so that we can measure its actual behavior. So again, the cell applies the pressure. We have these induced stresses. Now we're going to call these induced stresses delta sigma, or a lot of engineers use sigma d to imply deviatoric stress or deviator stress. So if you see either of those terms, we're referring to the RAM. Okay. So if we do a free body diagram of the soil, we can show you kind of what's going on with just arrows. Now, the triaxial test is going to have two stages. The first stage is what we call the consolidation stage. So here's my soil sample. Excuse me. In the consolidation stage, what we're going to do is we're going to apply our stress uniformly all around the soil from the water that's outside the membrane. And we can pressurize that water to the point where it's going to squeeze our soil sample and push water out of the void space in the soil and try to get it to shrink in its volume. By definition, that is consolidation. So what we do then is the first stage is we try to consolidate the soil to the stresses we think that it was feeling in the ground. It's geostatic stresses. So in terms of these arrows, we're going to call these sigma 3 because they're going to be the minor stresses. And when we first apply these stresses from the water, it's the same stress all the way around the soil because it's hydrostatic, and thus we say sigma 3 is all the way around our soil sample. Now in stage 2, this is the shearing portion of the test, and this is where we're going to try to mimic the induced stresses. So we're going to add the additional stress from the ram, and the summation of that ram stress plus the hydrostatic stress that was confining the soil in the cell anyway. That summation is now what we call sigma 1, or the principal or the maximum principal stress, and the stress from the water on the side of the soil sample hasn't changed, and so that still remains sigma 3. So just as review, in stage 1 we have just the cell pressure, and then we're going to imitate the geostatic stresses. In stage number 2 we have the cell pressure plus the ram. I can't help myself, I'm sorry. The loading ram, and this is going to imitate the induced stresses being applied to the soil. So I'm going to introduce you to 3 types of triaxial tests. We're going to talk about 2 of them today in this lecture. And the first test is what we call a consolidated drained test. Now, the names of these triaxial tests are very important because they tell us what we're going to do in the first stage and the second stage. The first word in the name is what's going on in the first stage. And the second name the second word in the name is what's going on in the second stage. And they're describing what we're going to do with the drains that are leading into the soil inside the membrane. So in the consolidated drained test, here's what's going to happen. We prepare our sample. Let me just show you. We have here a plot of time on the x-axis, and we have pore pressure inside the soil sample. Okay, so what's going on here in this amount of time? This is just going to be sample preparation, getting everything inside the membrane, getting things squared away. Once we get it inside the membrane, we flood the cell, we lock it off, and then we crank the pressure on the cell. When we crank the pressure on the cell, if we're watching a pore pressure gauge, during the entire early portion of the test, it should be around 0. And when we crank that cell pressure, just as we learned about in consolidation or primary consolidation theory, when the cell pressure squishes that soil, the first thing that's going to push back, or the thing that's going to take that new stress that we just applied, is going to be the pore pressure. Pore pressure is going to take it all. So we're going to see an immediate huge spike in the pore pressure in the soil. And so what's going to happen though is that water is going to want to get squeezed out. If we keep the drains open going into the soil sample, the water is going to exit through the drains, and as the water begins to exit, the pore pressure is going to go down, 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 down. Now as that's happening, the soil is consolidating, meaning that the effective stress, I'm not sure why that disappeared, that the effective stress is going up, and the volume is going down because we're pushing water out of our soil sample. And eventually we're going to get to the point where we still have our cell pressure applied, but our excess pore pressure is back down to 0. And it's at that point right there that we say now that the soil is bearing the load. The effective stress is increased and is now taking all of that additional total stress that we applied through our cell pressure. Once we get to that point, now we're ready to go into stage 2. So when I say consolidated, what that means is that the drains are open during the first stage, so that the soil can consolidate, its volume can change, and its effective stress can increase. Okay, that's stage 1. Now we're ready for stage 2. During, by the way, free body diagrams, this represents stage 1, meaning that we apply our sigma 3 from the cell. Our pore pressure is always going to be equal to 0, which means that we're not ever changing this sigma 3 that we're applying to our soil sample. And then our change in pore pressure, the goal is that at the end of stage 1, that pore pressure is going to equal 0, and that it's not going to change. It's going to constantly be equaling 0. We're going to have a flat line here by the end of stage 1. Okay, now during stage 2, we're going to apply the deviator stress. We're going to take that ram and we're going to start squishing our soil. Now here's the key. Usually, when you start shearing soil has the same effect that consolidation does. It tries to reduce the void space in the soil if it's a contractive soil and squeeze water out. Conversely, if it's a dilative soil, the soil will try to grow its void space and try to suck water in. So when you shear a soil, during shear stage, you're going to get some weird pore pressure effects. But in the second stage, because this is a consolidated drain test, we're going to leave the drains open, which means that as we are shearing it with the ram, if water wants to push out of the soil, it can. If water wants to suck in to the soil because of dilation, it can. The point is that the drains are open, and that's why we call it a drained test. So if the drains are open, then we would expect the pore pressure to remain at 0 during the entire portion of the shearing test until the end of the test, when a failure plane will develop in the soil and the soil is essentially failed. So the whole goal of a consolidated drain test is that we need to shear the soil at a slow enough rate that the water that wants to get out can get out, and that water that wants to come in can come in to the soil. Our goal is to keep the excess pore water pressure equal to 0 during the entire shearing portion of the test. So that's a consolidated drained test. So let's do a little cartoon to show you how that would work. Let's say, okay, here's my clay specimen. I get everything put into the membrane. Everything's ready to go. And now we're going to go ahead and apply the cell pressure. And as we apply that cell pressure, immediately we can say then that if we're going to plot, Mohr-Coulomb from this thing, we could say, all right, I don't have a circle per se, because all of the stresses on the top and on the side, they all are equal to one another. They're all equal to sigma 3. So my Mohr's circle is actually just a point. It's like a Mohr's point. Okay? So once my soil consolidates, then I'm going to apply the deviatoric stress, but I'm going to leave the drains open. So as I start applying the deviatoric stress, what's going to happen is the deviatoric stress is going to increase the stress on the top of my soil, but the stress on the side of my soil is going to remain the same. So we're going to start to develop a Mohr's circle, where the upper stress here is the maximum principal stress representing the stress on the top of my soil sample. So that circle, as we increase the deviator stress more and more and more, the circle is just going to get bigger and bigger and bigger, applying to my soil. Now eventually what's going to happen is we're going to develop a shear plane. A shear plane will develop in the soil, and that's the point where we say, okay, the soil failed. So let's say then that this deviatoric stress plus the cell pressure is going to equal that combination of stresses right there. That's going to be my sigma 1 at failure. When you see a little F there, that means that's at failure, and that's going to be sigma 3 at failure. So then we would assume that this guy right here is the Mohr circle that must be touching the failure envelope. So I know that my failure envelope has to be tangent to that circle. So if we're testing a sand, we know that the cohesion is certainly going to be equal to 0. But here's something that's interesting. If we're doing a drained test and we're not allowing pore pressure effects to occur, even if we have a clay, quite often cohesion is also going to equal 0. Why is that? Because cohesion really is, it's more a phenomenon that's related to pore pressure. And if I don't allow pore pressure to build in the soil, then quite often my cohesion, even in clays, are going to be equal to or very close to 0. So I would then say, as we indicated before, that's going to be my maximum principal stress at failure. And then, as we did before, we could find the pole for this particular Mohr circle, and the pole is going to be right there. And if we take this failure line and just transfer it up to the pole, that failure line is not coincidentally going to touch Mohr circle right at the point of tangency, where our Mohr circle touches the failure envelope. So thus we know that those are the stresses acting on this plane right there, and those are the stresses that cause failure to occur. So the consolidated drain test is going to give us what we call the effective strength of the soil. And what does that mean? Well, what that means is that this goes back to this equation. Effective stress equals total stress minus pore pressure. Total stress is what we apply to the soil through the ram. But if pore pressure equals 0, then that means that the only thing that's resisting that applied stress is effective stress. So that's why we call this an effective stress test or an effective strength test, or in other words, a drained test. It's drained because the excess pore pressure is always equal to 0 in this test. This failure envelope then that's produced from this corresponds to the what we call the effective stress or the drained failure envelope. And we distinguish this by this term right here. Do you see how this phi has a little apostrophe there like the effective stress does? So whenever you see phi prime, that means that it's the drained failure envelope, that it represents the shear strength of the soil when the soil has had enough time to drain and there's no pore pressure effects that are messing with the strength. The strength that you're measuring is the interparticle shear strength of the soil. That's what this friction angle means. So here's a cool little picture I thought you might enjoy. This is a picture of a test of clay that was performed in a consolidated drain triaxial test, and you start to see failure bands, right? You can see a failure band right there, but isn't it cool that you also see an inverse failure band at the same angle, and they're crossing right in the middle of the soil? That tells you that we're getting uniform shear stress loading through the whole soil, which you remember when we talked about the direct shear test, we had stress concentrations right at the boundary, but the stresses in the corner weren't the same as the stresses were in the middle of the soil. That's not the case with the triaxial shear test. We get uniform stresses throughout the soil profile. Okay, the second of the triaxial tests I want to introduce you to is called the consolidated undrained. So again, consolidated refers to stage 1 of the test. That's a goofy looking one. Stage 1 of the test. And the undrained refers to stage 2 of the test. And we call it CU for short. So here's how this is going to work. Again, like before, we're going to have our sample prep period where we get the soil inside the membrane and get everything ready. Once it's ready to go, we fill the cell and then we crank the pressure on the cell. And like before, the pore pressure inside our soil, in the soil that's in the membrane, takes that load. But we leave the drains open during stage 1, which means that the water can squeeze out. As water squeezes out, pore pressure goes down, effective stress goes up, and volume goes down because it consolidates. Okay, once we get down to 0 pore pressure, that means effective stress is equal to the total stress that we just applied from our cell. And we get ready for stage 2. Now, here's the difference between the last one we talked about. In the CU test, stage 2, we're dealing with undrained conditions, which means we're going to close the drains. A couple things happen when we close the drains. First of all, pore pressures will not equal 0. They can be positive, they can be negative, but the point is pore pressure is going to start doing some wacky stuff. The second thing is that the volume has to maintain constant. So the change in volume is going to equal 0. Why can't the volume change anymore? Well, we close the drains. The way that the soil volume changes is it pushes water out of the voids. But if we close the drains, water can't leave the soil anymore. And so the volume of the soil is going to remain constant. But what's going to start changing now are the stresses that the soil feels because of these pore pressure effects. So once we start shearing the soil with the drains and the valves closed, the pore pressure effects are going to start going wacky. If they start going positive, that means that we're going to have a contractive soil. It's contractive meaning the soil is trying to push water out. The water is trying to get out, but it's jammed up against the closed drains. It has nowhere to go, so the water pushes back. And so we get positive pore pressures. Conversely, if I see pore pressures that do something like this and go negative, negative pore pressures mean that I have a dilative soil. Dilative meaning that the soil is trying to expand its volume. It's trying to get the void space to get bigger. And the only way the void space can get bigger is if it sucks more water into it. But the drains are closed, so it can't. So it creates a vacuum inside the soil, and we get this negative pore pressure. Now, what types of soils are generally involved, or what types of soils are generally contractive? So these are going to be like loose, cohesionless soils. So like sands and gravels. Those are going to be contractive. Also, normally consolidated clays are going to be contractive. Conversely, soils that are dilative are going to be like dense, cohesionless soils. or over-consolidated clays. Those are soils that are going to demonstrate dilative behavior and negative pore pressures. So that's how the test is going to look in terms of pore pressure effects that we can measure. Now, the CU test is useful because we can get two different failure envelopes. The first failure envelope, oops, let me erase some of this stuff. Looks like I've got some additional notes popping up that you guys will want to see. Okay, we talked about consolidation or contraction. Contraction, same thing. And dilation. Okay, the first failure envelope is what we call the undrained failure envelope, or this is also known as the total stress failure envelope. Same thing. Remember, what we said was that effective stress equals total stress minus pore pressure. Okay. Now, if we could change this around, we can say total stress is going to equal effective stress plus pore pressure. If there's pore pressure effects in there, then the effective stress is only going to be taking part of the load, and the pore pressure is going to be taking the other part of it. And that's the reason we call it a total stress test. There's pore pressure effects still in there. So this envelope still includes the effects of excess pore pressures acting on the soil. And this is going to represent the soil behavior when the soil is still adjusting to a new induced shear stress. So like say in construction, if I go and I dump a big pile of fill on top of the soil is immediately going to feel that new stress. And the soil is going to try to either contract or dilate, but it hasn't actually completed it yet. So in that period where it is trying to dilate and contract, there are pore pressure effects, these types of pore pressure effects in the soil. And for that brief period, the soil is acting in an undrained manner. And so if we're interested in predicting the soil shear strength at that precise moment, then we're going to use the undrained failure envelope. The second one, though, is what the drained failure envelope. This is the same one we had before. This is the effective stress failure envelope, like what we got from the consolidated drained test. As before, this envelope is the one that has the phi prime, has no excess pore pressure effects, and we're saying that the effective stress is equal to the total stress. But how are we going to get that envelope from this test? Because we do have pore pressure effects. Ah, good question. Well, the answer is effective stress equals total stress minus pore pressure. If I know my total stress because I applied it, and if I know my pore pressures because I'm measuring them, then I can correct my calculations to subtract out the pore pressures and get the equivalent effective stresses as if no pore pressures were actually present in the soil. So doing that, that's how I can get the drain failure envelope. So what I'm trying to tell you, folks, is that the CU test gives you two tests. It's like doing two tests in one. We get an undrained failure envelope, and we also get the drained failure envelope. So let me show you in terms of a little cartoon how the CU test is going to go down. Here's our clay sample like before. We get it prepared in the membrane, we put it in the cell, we flood the cell, and we pressurize the cell. And we leave the drains open and allow the soil to consolidate. And once it consolidates, that gives us our point on our tau sigma axis like we had before, and we wait until pore pressure equals 0. Now once pore pressure equals 0, we're going to close the drains. We're going to close the drains and lock in the volume in that soil. And then we're going to apply the deviatoric stress, the deviator, the RAM. And as we do that, the deviatoric stress is going to increase, but at the same time we're going to be measuring using a pore pressure transducer the change in the pore pressure that occurs. Now, if I plot just the total stresses, okay, so these are just going to be the stresses that I'm applying to my soil. So the cell pressure and the deviatoric stress, as before, I'm going to eventually end up with a circle. Well, the circle is going to get bigger and bigger and bigger and bigger as it did before, until eventually I'm going to get a circle when we have a failure plane develop in the soil. That's going to be our total stress circle, okay? But, well, and then we're going to say that the undrained failure envelope, or phi-T, the T stands for total stress. Okay, that's going to be the failure envelope that governs this behavior. Remember, this is our total stress Mohr circle. Now, if we correct Mohr circle for the pore pressure that we measured, what we're going to do is we're going to like shift this whole circle over, and we're just going to shift it by the amount of pore pressure that we measured, because remember, effective stress equals total stress minus pore pressure. Total stress is this circle right there. This pore pressure is the change in pore pressure that we're going to subtract from our total stress. So the effective stress is going to be this circle right here. So all we're doing is we're shifting our circles. And once I have the effective stress circle, this circle that I'm highlighting right here, this circle is going to represent excess pore pressure equals 0. In other words, the effective stress equals the total stress. And so what that means then is if I draw a failure envelope that's tangent to this circle, this is going to be the same failure envelope that we got from the CD, the consolidated drain test, where we have phi prime. So this is what I mean by the two different failure envelopes we get from the same soil. This failure envelope represents the soil while it's draining. This failure envelope represents the soil after it's drained. And depending, I mean, you know, and I know that this concept may be challenging for you students to try to grasp right away, but think about it this way. We're not just designing the embankment or the building to stay standing after it's constructed and we walk away, you know, 20 years later. We don't want it to fall down while we're constructing it either, right? And if soil shear strength is governed by the effective stress of the soil, well, the effective stress is governed by the pore pressure. Therefore, if my soil is experiencing funky pore pressures, whether that's from consolidation or from shearing, those can mess with my effective stress and thus mess with my soil shear strength. So we may want to account for the periods in the soil's existence where it is experiencing draining and it has those pore pressure effects in there. That's why we have two failure envelopes. Now, interestingly enough, the failure plane that develops in the clay is going to be the same failure plane that corresponds to the drained or the effective stress failure envelope. It's not going to be this one right here. Do you see how that slope angle is different? It's a little more shallow. Okay, that failure plane is a false. Goodness, I can't write today. Let me try that again. It is a false failure plane from the total stress circle. So just ignore it. We don't have to worry about it. The one that's real comes from the effective stress circle. And that is because soil is governed by effective stress. Okay. So, what's the moral of this story? The presence of excess pore water pressure is the only difference between the drained and the undrained envelopes. It's that this one is still draining, this one has finished draining. That's the only difference why those circles change and shift. Think of it this way. When I apply my load, this is what my soil initially fills, and then it starts moving towards this circle. And once it reaches that circle, that's where it's going to stay. So let's look at a couple of examples. Here's some, if we're dealing with sands, where we know that the cohesion is roughly going to be equal to 0, then we would expect our failure envelopes to look like this. So here's my drained failure envelope. Here's my undrained, or my total stress failure envelope. And thus the total stress failure envelope corresponds to this circle right here. And the effective stress failure envelope corresponds to this circle right here, which means that in order to get from total stress to, or undrained to drained, that everything had to move to the left. And remember our equation, right? That effective stress equals total stress minus pore pressure. So if I'm moving to the left and reducing my numbers, that means that my pore pressures were positive. I had positive pore pressures, so everything moves to the left. Now if I had a dense sand, what I'd be saying is that pore pressure would be a negative value. So if I have a negative value and I subtract a negative, then I actually get a positive. So if I have a negative pore pressure, what's going to happen is my drained failure envelope is actually, or my drained Mohr circle is actually going to move to the right of my undrained. And what's going to happen is if my circle's over here to the right, and that's my drained, then my drained failure envelope may actually be lower than my undrained failure envelope. And that makes sense if you think about it. If my soil has a vacuum going on inside of it that's artificially increasing my effective stress, then my soil's shear strength is going to be artificially increased temporarily as well until the vacuum goes away. And then my effective stress comes back down to normal and normalizes itself. So, what am I trying to say here is that the change in pore pressure is going to be positive for loose sands. And if it's positive, then my drained Mohr circle is going to move to the left from my undrained. Now if I have a dilative soil, my change in pore pressure is going to be negative. And when I subtract a negative number, I get a positive. So that means that my drained Mohr circle is going to move to the right of my undrained Mohr circle. So that would be like for a dense sand. For clays, things are a little more complicated because we have the pre-consolidation pressure we have to worry about. Now, do you remember when we said for a direct, let's go to the whiteboard, when we did a direct shear test on a clay, and I showed you that given the pre-consolidation pressure, that if I'm at stresses greater than the pre-consolidation pressure, I'm going to have one particular friction angle, such that if I extended it out, it would roughly go through the origin. But once I test at pressures less than the pre-consolidation pressure, it's like my failure envelope changes. The slope of it changes. And we end up with some cohesion in the soil, right? Same idea. What we see is if I perform a CU triaxial test at stresses that are less than the pre-consolidation stress, so the soil is over-consolidated. Remember, OC clays are dilative, which means that my change in pore pressure is negative, which means that my drain circle is going to move to the right from my undrained circle. So you can see that's why the drain circle here is to the right of the undrained circle. Now, if I run my test at confining cell pressures and consolidated at confining pressures greater than the pre-consolidation stress, I make my soil normally consolidated, so it's not over-consolidated anymore. And normally consolidated clays tend to be contractive, which means that my change in pore pressure during an undrained test is going to be positive. So if I subtract a positive number, I would expect then that my drained circle, shown here, is going to be to the left of my undrained circle, shown here. So if I'm testing my clay when it's normally consolidated, I expect it to be contractive, and my drained friction angle will be higher than my undrained friction angle. If I'm testing my soil when it's over consolidated, then I expect it to be opposite. I expect my undrained friction angle to be or my undrained friction envelope, to be greater than or above my drained failure envelope. You see how they have a crossing point right there? So, not that I want you guys to drastically grasp and understand this concept. We'll talk more about this when we get into advanced soil mechanics in 641. But I want you to kind of see that depending on whether or not we're over consolidated or normally consolidated, the soil changes its behavior from contractive to dilative. And it's the same clay. The only thing that changes is how we consolidate it and confine it in the triaxial test. So I'm not going to walk through this example with you, but I want you to take some time, pause the presentation, and walk through this solution. This solution, they're giving you a soil sample here, and with all the pressures that they're applying, and what they're asking for is the consolidated undrained angle of resistance. So this is going to be the total friction angle, and then the drain friction angle. That's the same thing as saying phi prime. So pause the presentation, go through and see how they solve this. And remember, it's a saturated sand, so we can go ahead and assume that C is going to be equal to 0. And that's why you see all of these failure envelopes going through the origin there. Okay, so that's all I have for this lecture. I know that this is a lot to swallow, folks, so don't be shy to watch the presentation a few times or to go back through the concepts or things that I talked about that may be confusing to you. And don't be shocked or shy if, by the way, you're feeling a little overwhelmed or you have a headache because I'm trying to explain the idea of pore pressures to you. Pore pressure effects in soils are very complex and are complicated, and you have to chew on them for a while and think about them to understand the difference between contraction and dilation, pore pressure effects, and those kinds of things. So if you're feeling a little overwhelmed, don't fret. Everybody does. You're fine. Just think about it and digest on the things we talked about here. And as you do the homework assignments, hopefully understanding will start to kick in. But I appreciate your guys' attention. Have a wonderful day, and I'll see you in the next lecture.